The gas is itself
Disconnect.
inside.
Direction. This is a silly
Go on,
thing
go on,
to talk
Jeremy.
about.
You can take over. Yeah, this is where the ignorance kicks in.
Brummy, he's saying shit like they're facts, like gas inside the container is a downward vector. They can't prove that for one.
Exactly.
You can't prove that. Why?
Sorry, Jeremy. How is that not evident?
This is silly, dude. Like,
it just proves my point.
They sell gas
Look, the way you're spiraling. You're spiraling.
If you guys talk to people who work in these industries, you would know this to be true. If you want,
I'm talking to you though, Kosho. I'm talking to you. You asked me a question. How does it? How's it went? You are proving my point right now. You are proving my point because you asked me.
If you want to go buy helium right now, they would sell it to you and they would show you how much helium is in there by showing you the weight. That the weight
Your globe tardation.
It's empty by
your
it has less
globe
weight.
tardation right now is kicked in, and I've told you. You asked me to give you an example of when a globe is not willing to face something that contradicts what they truly believe.
But it's not a contradiction.
It is a contradiction. How the fuck do gases have a downward vector? You said, "Oh, we can weigh them." I've just pointed out that you've put them inside a container to weigh.
Okay, and I'm asking, how does that change? How does that all of a sudden give it weight?
That's why the world is not a globe.
That question. How does that magically give it weight? When you could show me that, then I have a reason to say that you contradict something was contradicted. Otherwise,
weights don't have a downward vector. They don't have a downward bias. That was the question. They don't have weight. They don't have a downward bias. You're now subscribing a downward bias to them. Well, no, it's not. Weight is just basically the amount of stuff or something. Yeah, you're trying to say it's a downward vector. The only way you can weigh a gas is by putting it in a container. A container has a downward bias, but not yet. A container also has weight, but you call weight, and a downward bias a totally different thing. It's a totally different thing. It doesn't have a
give it weight if it didn't have it otherwise.
Because it's a solid. It's not a gas.
I'm not saying what is it made out of. I'm saying how does it magically give it a weight?
This is. I can't get into
because it contains.
Can't be
Kosho, you can't. First of all, you were spitting shit like they were true facts. The gas inside the container, you can't prove has a mostly downward vectors expanding all throughout. The only reason it weighs something is because now we've trapped this amount of gas, and we can
Jeremy,
put it on the scale.
Ask you a question is. When you have a positive number, is this a positive value? I'm just going to answer for you. The answer is yes. When a number is positive, that means it has a positive value. That means that if they have gases in a container and there's a positive weight increase on the scale, that means that the net force downward is greater than the net force any other direction. So what this tells you is that the gas indeed has weight in a downward vector. It's silly to
Can I join in? Can I join in for 1 second?
Please.
I think one of the things that we could do, which would be kind of indicating that it has weight, we can weigh, like, let's say something like carbon dioxide, frozen carbon dioxide. We'll see that it weighs 1 gram. I put that 1 gram carbon dioxide chunk inside of a container, and I let it melt into a gas. It will still weigh 1 gram more because carbon dioxide has weight, whether it's in solid state, its liquid state, or in its gaseous state.
When it's in the container. Yeah, sure.
But answer the question that I asked before then, Jeremy. What is it about a container that magically gives things weight?
Maybe you need to use your own brain to figure it out. Because you've been told the answer over and over and over, and you're still not getting it.
Agree that none of us have an answer to that. Not you, not
me. You do have an answer for it. I've told you the answer to it many times before. There is an answer to it, and I feel you need to sit down and think about it critically, and then realize why.
I know you're a man, Brummy. So be a man, and either tell me what the answer is, because I'm being humble right now and saying I don't know what the answer is, Brummy. Be a man and tell it to me, or be a man and realize that there is no answer to it, Brummy.
There is an answer to it, an absolute answer that I've told you. I've told you the answer thousands and thousands of times, and you're still asking me the question like you haven't heard it before.
You told me how containers give things weight.
Containers are made out of solids. A solid and liquids, they do have a downward bias. They do have a downward vector. Look at the world that you live in. The solids at the ground. Then it goes to water. Then you have your gases. Then your light gases right up in the atmosphere at the top of the, at the very top. Helium, hydrogen, nitrogen. That's what's all up there. So for you to sit there and say, "Oh, gases have a downward vector," when they're fucking up in the highest fucking parts of the world, it's just so stupid.
Right, so
obviously they don't have a downward bias. Otherwise, the gas would be on the floor.
Yeah, a solid container, does have a downward bias, as you just said, and guess what? That downward bias is accounted for when you put an empty container on a scale. The problem is when you press the button on the scale that zeroes out the weight, and now it zeroes out the weight of the container of whatever.
Yes,
When it's
I
empty,
know where you're going
and
with
you
it.
put
It's called
helium in it.
tearing.
It has a positive value. That's not
Well
accounted
done.
for by the container.
Well
Okay,
done.
you're
well
saying.
done. Well,
This is the
well, look, hold on, no, Jeremy.
Answer
Let me
only
just
that
say,
question.
Jeremy already told you the answer to the question. He already said it to you. He says you are containing that gas. All right, maybe tearing off the actual weight of the container. I get where you're coming from, but the actual behavior of the gas and the nature of the gas is still captured and being forced in a particular direction by the container. And that's as simple as what Jeremy said
Why
earlier.
is it forcing it down?
Oh my God, it's over. Zan, hold on. If it was the amount
That
of
makes
gas
no
particles,
sense. You've been saying that for months now. It makes no sense.
Next question is the exact question I was going to ask. Why is the downward vector the prevalent one? If it goes in all directions, why would
It's covered. I'm triggered.
I mean, don't do that. Why would the net forces not equal out? Why would there be a net positive one downward?
Asking it. Use your own brain.
This thing only had weight because of because most of the gas particles are pressing down, right? That's why you say it has weight.
Of course it is. They have a higher velocity down.
Stop. I wasn't done.
Hold on. Not more.
I was almost done.
Let me just give it to me.
Zanik, we'll all get complete turns. All complete turns. Let him have his complete turn, okay?
But he doesn't seem like he has a complete...
You're going to go right after him, Zanik, but let him have his complete turn. Come on.
Okay, you guys are saying that there's gas particles going mostly down, and that's what's giving it its weight when it's on the container, when it's on the scale. But if that's the case, then the shape of the container would matter, because you could have a long, thin, skinny container or a tall, huge container. There'd be different amounts pressing down on the bottom of the container on the scale.
Yeah, that's right.
Okay. Now I see your confusion, and this follows, and it's consistent with how you've confused us ever since we first started talking about it. Pressure is the force per unit area. Now these higher velocity molecules that are traveling downward faster, they're omnidirectional, like Witsit likes to say, omnidirectional. Yes, they're going in all directions, but when they come down, they're going faster. They have more momentum when they're going faster. And when they hit something, they have a change of direction. You know this, and by definition, a change of direction is a change of momentum, which is an increase of force, which is a force defined. So the force down is going to be whatever that velocity is in that molecule. You have a long container, you have a doesn't change. Make it really narrow and tall, still have the same force per unit area down.
Right. But if the non-force of gravity is resulting in this force of gas or whatever, shouldn't we just talk about the force of the gas itself, since we have an actual force there but no force with gravity? Why don't we just talk about the gas itself and the medium that it's in or whatever?
That would be consistent with thinking that it goes in all directions evenly. But because it doesn't, because the gas actually has weight. So when it goes down, it is actually accelerating downward. When it's going upward, you can say it's, quote, decelerating, going upward. Always going faster down, and always will impart a greater force on the surface.
I think Zanik, the easier thing to say is it's an indisputable fact that if you stick a pressure probe at the bottom of the container and the top, there's going to be higher pressure at the bottom than at the top.
Hold on.
Game over. The gas has more force on the bottom. That's all you need to know. You don't need to talk about anything else.
I gave the description, and Jake just gave the actual distilled title of the book.
All right.
Boom. Done.
All right, let me run you guys through a hypothetical. Say we had a container and we had one gas molecule in it, and we could weigh it and we could register it. All right, weighs a little bit more. We got one gas molecule in this container. You think it's going to hit the bottom more than the top?
Stop saying that. Stop saying more. I corrected you many times before, and I'll correct you again today.
Okay,
it's not more. Listen.
The one gas.
Hold on.
With the
it's
one
not
gas
more.
molecule, address the one gas molecule in the container.
Sure.
Jeremy, Christ's sake, it's coming down always faster.
It's like Jeremy, think of it like a basketball, or a better would be like a hand court ball, right? That's really bouncy. I could throw it into the ground just hard enough to where it hits the bottom of the ground hard and it just barely kisses the roof. Like let's say it's in my room, right? I can throw it down so that it hits the ground hard, but then it just barely kisses the ceiling. And then it comes back down and it hits the ground hard and it bounces up and then it barely kisses the ceiling.
Jake,
All right.
It's
Jake,
hitting equally on both sides, but it's putting more force on the bottom.
Jake,
All right, all you
this
have
just
to
reminded
do
me of
is-
a great analogy. Can I build on that, Jake? Let me build on that first.
Yeah, go ahead, go ahead.
You know when you have a ping pong ball and you it's bouncing and you hit the ping pong ball, and as you move it downward, the ball goes real fast as it stops, right? When it goes down, it's always going to hit the surface of the table greater than it's going to hit the top of this paddle. That's what Jake's saying right there. Does that make sense?
Okay,
The force
all
will
that's
always be
all
on the
that's
bottom.
left to do is for you guys to prove that this is actually happening. So Kosho
We
and Moyak
do.
need to
We
get their
actually
heads
do.
together.
We've
No,
already
they don't,
given you.
because they're. Why are Kosho and Moyak in the middle of trying to prove this if you say it can be proven already? Let's see it then, and you can save them a whole bunch of time and money.
Because they're stubborn people, not because it needs to be proven, because they're stubborn people who, even after we're done showing this to them, are going to still persist in their belief about it. So
It's because
Zanuck
we're
thinks
trying
he
to
can already
answer
show it,
your
though.
moronic question.
Zanuck thinks it's already proven, though.
no,
So let's see
Jake,
it.
did you hear what Jake said when he piped up? He first came
Yes,
and he
the
said,
ball and the.
"Why are we even? Why are we still talking about this? Gases," this is what he said. Gases are they have a higher pressure at the bottom than they do at the
Not,
top. This is known. This is on the same level as them having weight at all when you put them in a container, and being able to measure helium, for instance, by knowing that it has more in there when it weighs more. So when the thing that you're describing and going in all directions, you have to put this in your head that for it to be having a net force upward, that means that it would have a negative weight when you put it on the scale. For it to be equal in all directions, it would have no difference when you fill it with helium and put it on the scale, because it would be acting upwards equally as it's acting downwards. When you put it on the scale, it has a net force that is positive in the downward direction. This is evident that there's a downward bias in these gases. It's a very apparent thing.
no, that's
And I'm
your.
sorry for getting frustrated with you guys, but it's because it's one of those, it's like so apparent and so obvious.
Simple, very simple.
Yeah.
Everything's obvious to you guys with the pen with the.
You've shown us your confusion by talking about the long. Do you understand what the long container on a scale versus
Yes.
the tall container?
I understand. I understand. Yes.
Show me you understand by explaining why that now by what we've told you. Please tell us by what we've told you how that's possible. How the wider container, which has a longer surface area in the bottom, can create the same force on the scale as the tall container, tall narrow container.
Because
Please
the
tell us.
tall
Go ahead.
ones are going down faster.
No,
What do you mean no?
come on. So you didn't. You did. So you think you know something and you can't even tell us. Tell it to us. That's the problem. See, when we tell you things and we think you understand, you really don't. And then you
I
say
already moved past this.
No,
in
no,
my head.
but that's-
I
what you
understand
want-
what you said.
But that's critical.
What you want to know?
Critical.
What
That's
you wanna
critical
know?
to understand why.
What
I tried to explain it. I put it in simple terms. Why the long container sitting on the small scale versus the very, very tall container, with a point maybe at the bottom, sitting on the same scale. Why they produce the same exact weight force.
That's a good point. No, hold on. He asked the question. It's a great point, because basically that's the point of where all the concentrated matter is going downwards, and it's going to that actual point where it receives on the actual scale. So obviously, if you had that long piece, for example, that long container, leaning on the floor, so what it would take some of the pressure off that's to be on that pinpoint. But if you've got it all pinpointed onto the scale, then everything will register to that point, because the whole container contains everything within that container and puts it on that scale in that pressure point. Hence, exactly why you guys need to open your fucking mind and understand
Wow.
that's why
And
gases
he just
will
said
come
that
onto the scale.
they weighed the same. It sounds like you were arguing why they would be different. Zanuck is saying that those
you're not
two
listening.
scenarios, they weigh.
Listening, Kosho, you didn't listen to what I said. Right? So that's why you thought that. You've got it wrong. I said if it was long and some of the scale was off the scale and leaning on the floor, then it would weigh less, because
No,
it would be on
it has
that
to be on
pinpoint.
the scale.
Both scales are going onto the
Not
scales.
saying that.
The
They weigh
scale.
the same.
Yeah, we did. You said they were weighing the
There's a
same. You're
segue to
confusing
this.
it. You're confusing it,
Hold-
Kosho.
Bromy,
You confused
stop.
what I said.
Stop and you might learn something.
I already learned.
So-
Kosho
No, you're
confused
done.
what I just
Bro,
said. He didn't.
consistently
Kosho
you're
didn't listen to what I said, and now you're trying to run with me.
did.
Oh, God, Brody
That's-
didn't
that's
understand. You've just proven your own point. You just debunked your own shit.
Don't try to talk over this screaming gorilla. But Brumming, go ahead and just say again, so we restate what you're saying.
Right,
so
you've just proven to yourself now with that example exactly why gases weigh on a scale. That's what you've just proven. Nothing to do with gravity. You've just proven your own point to yourself. Now you realise it. I'm glad that you realise it. So don't try and muddy the waters. Don't try and confuse what I just said.
I gave you the opportunity to elaborate what you're saying, man.
No. Well, I elaborated it. You confused it intentionally.
You're making a claim about something that nobody in here believes.
The claim that he said about the two, he said the two different sorts of containers, one being long, one being short. They both will weigh the same. That is literally evidence towards my point of why gases weigh on a scale, even when you tear them. Well, because you don't use your brain and think to yourself. That's why. You're not a critical. Because you're not a critical thinker. This is why they're not the same. Because you're not a critical thinker.
They're not
I'm telling you.
If you're not going to address the question,
you're not a critical thinker.
Answer the question, bro.
Because you're not a critical. That is the answer. That is the answer. Because you've never been taught how to think for yourself. You've been taught.
Please just answer the
question. Mute me then. Yeah, Fundy, mute me then.
Answer the question.
That's my answer. My answer is. My answer is you have never been taught to think for yourself. You're a sheep.
That's not the answer.
Just answer the question, man. Why do they weigh the same then?
That's my answer. You've never learned to think for yourself. That's my answer.
That's not an answer to the question.
Disengage from the conversation, please, Brumming. But we're going to talk with Jeremy or other people who are actually talking about this stuff. What Zanuck had said was, they could be laying down, it could be standing up. They're going to weigh the same. I'll tell you the reason why they weigh the same. I'm a man.
Well,
I can do that. They weigh the same because they have the exact same amount of mass. And the weight is equal to the mass times acceleration, which is the same for both of them as well. So in a simple mathematical equation, A equals to A. They equal the same thing because they are the same thing. It's not that hard to answer. Yeah.
There's another.
I think
Can I add to that, Coach? There's an interesting aspect of that as well. So if you have this container that's laying down and you have a certain amount of mass in there, it'll have a pressure differential from the top to the bottom, and it's really long and flat. It's on a scale, and it weighs 1 kilo. Now we have this, and we squished the container and stretched it up super tall like a pole. Now the containers and the mass inside, as Coach just said, still weigh the same, but the pressure now inside is a differential top to bottom, and that's also indicative of why this thing has weight on the point or the bottom of this container that's very tall, because the velocities are going down and the pressure, which is the force per unit area, is acting on this scale in such a way that it gives the exact same weight.
I was gonna say,
your guys' critical thinking skills are just lacking, just slightly. Just lacking just a bit. That's all.
Right. So I thought it was Zanuck who made this point, but I think actually it was Moyak who made the point. I was gonna praise. It was a good point about having let's say water. Water's a good example. You put water in a isolated system container, and it's ice, and you transform that into water, and you transform that into steam. You're gonna find something that most of us won't find that surprising. A few of us might even lie and say that it's not happening, even when they see it happening. But what's gonna happen is these things are gonna weigh the same thing in all three cases, because these three things in all three cases are the same thing, have the same mass, and therefore have the same weight when they're liquid, solid, or gases. As long as none of it's leaving the container and you're not losing it to the atmosphere or whatever, these three things, no matter what state they're in, are going to weigh the same. I wish that these things weren't the focus of what we have to be. These things we shouldn't have to argue about. These things, like, do gases have mass? Do masses have weight? These are things that, like, no, I'm not gonna rant about that. But just
I used to do refrigeration, okay, and in the refrigeration field, heating, air conditioning, you weigh your tanks to find out what's in them, okay. So you can lay the tank on its side or you can stand it up. You're going to get the same reading. It doesn't matter in that sense. Matter of fact, if you remember how Teflon was invented, the guy put two different refrigerants in a container, and then he went home that night. Now, before he left, he weighed how much he put in the container, and in the morning, he opened up the valve to do a test on this new refrigerant mix that he made the day before, and nothing came out. And that got him thinking either he had a leak in the container or something else happened. Well, something else did happen. The two refrigerants joined together and became Teflon. And he figured this out because the tank still weighed the same as the night before. Out.
Okay, you guys can't prove that the gas is going in a mostly downward vector.
Fluorine in it though.
You can't.
Well
Not
said,
looking down.
Jeremy. Well
So
said,
not where
Jeremy.
the
That's what it
force on
comes down to.
the bottom. Hold on. So the difference
Ironically.
between the gas, the liquid, and the solid ice is that we have those things are stable. The Coulombic bonding is what holds these molecules together in liquids. We don't have the Coulombic bonding with gases. They're moving in all directions, like you guys love to say. But why is it in the tank we have a pressure that is greater down? That is a force you can actually measure on a scale on the downside, not on the upside, because it has weight. So if you were able to get a super sensitive scale that could measure forces in nanoseconds, it wouldn't be like the liquid, it wouldn't be like the solid, it'd be like a vibration. And it'd be the molecules hitting the bottom with greater force than the top. So the average weight would be the same. So it's different with a gas than with the solid or with the liquid, in that the gas is bouncing off the bottom. Not making constant contact, it's making rapid contact. Very, very fast. So if you had a very sensitive scale, you could then measure that. It'd be a vibration, and the average would be the weight. Just like you can weigh yourself if you're in that tank and you're doing jumping
Well done,
jacks.
lads. Well done. You're
Hold
just
on,
preaching what you learned at school, Danix.
Hold on. 1 second.
Hurry up then, man. Wrap it up.
Hold
Wrap
on,
it up.
1 second. My turn still. I'm still talking. So if you did jumping jacks in that container on a scale, the scale would then weigh more than your weight and then zero weight. More, and the average would be
Okay.
Hold on. I'm almost done with the period. Your average weight would be your weight. You see how that works?
Yeah. I walk into a room, I stand on some scales, yeah? And my weight comes up on the scales. I stand off the scales, and guess what? The weight comes off the scales, and then I get from the scales, and I'm so smart because I talked about getting on and off the scale.
What are you
That's basically
talking?
what you just did.
No. I said if you're inside of
What
a
you
tube,
just did.
if you're inside of a tube and it's on the scale, you did jumping jacks. While you're jumping, you're in the air, the scale will be zero. When you make contact,
Yeah,
you'll be
well
hold on. You'll be more than your weight.
Well
and
done.
the average would be your average would be your weight. That's what the gas molecules are doing. They're making frequent contact with high velocity and a high force, but it's not constant. That's
So
how
what you're saying is
That's
so
how
what
we
you're
know-
saying is inside of a
that's how we
container.
know the velocity is.
So what
that's how we
you're
know-
saying is
Broomy, what the fuck's wrong
what you're
with
saying
you?
is inside of a
Are you
container.
brain
You're
dead
getting,
surgery? Have you dropped
what
on
you're
your
saying
head?
is inside a container, you're getting an average weight of the gas. You're getting an average weight of the gas. Is that what you're saying, Xanix?
Yes,
that
when
makes-
you can technically, when you're weighing gas, you're getting the average force imparted on the container. Yes.
You don't need to monologue. It's just So what you're
Is that
saying
the
is there's an average
monologue?
weight in the gas.
You have the attention
Well,
span of a fucking housefly? That's a
I have
sentence.
to make sure keep on. You need to be kept on a
Shut
tight
it.
leash, Alex, because you
Shut
don't
it.
stop
Hey,
going.
shut your mouth. Come on.
You're worse than Lemon Bird. Look, the fact of the matter is, you say it's an average weight inside the
Xanax. I'll actually stop whenever somebody's interrupting me or I go on for a while. Xanax has to get out what he's saying. He's kind of like right the hand in that he has to have the last word and control the conversation.
No, I just have to make my sentence heard, and then I'll
All right.
stop like I'm stopping now.
Okay,
we get the point. Sorry, we get the point of what you're saying halfway through. So once you're halfway through what you're saying, I got the point. I got the gist of what you're saying. Now let me respond to that gist. No, I need to finish off the rest of the book. You've made your point. Like you've made your point. That's all we need is your point. And you're saying you're getting an average weight of the gas. You're not getting the true weight of the gas. You're getting an average amount.
That is
Because
the true
gases
way.
are omnidirectional.
That is the
So
true
gases
way.
are
yes.
so gases are omni. No, you just said you're double speaking now.
But Brahmi, if gas has an average weight, then that means it has a weight, right?
Look, weight, yes, but just gravity, no. I know what you mean when you say weight, but what I mean when I say weight are different. When I say weight, I don't mean what you mean when you say weight. You think weight, therefore gravity. But
What do you mean?
But let's go back to what Janek's saying. Let's go back to what Xanax is saying because we need to establish that what he's just said is actually what I'm arguing. Yeah, gases have what you're weighing is like that container's dominated the gas, forced it on the scale, and even though the gas is still omnidirectional, what's been forced on that scale is still just not the actual true weight of the actual gas. Gases don't have a downward bias. They're inside a container. Now, if we had a large balloon, you're still getting an average weight that's going onto the cell, because let's say a balloon's quite a thin layer of solid and it's containing the oxygen in there or the air that you've blown into it, and then you put that on a scale. The gas is still going in all directions. You can physically see that by the shape of the balloon.
Now? Who's monologuing now? You tell me.
Sorry?
Who's monologuing?
Definitely me.
Okay.
Definitely.
Here's the problem, though, Brummy. If you have a gas that's heavier than air, you can just pour it onto a flat plate scale that doesn't have any sides or roof, and it will still register an increased force on the scale.
That's true.
As you're pouring it on.
That's true. And that's why it's important for you guys to get your critical thinking hat on when you're doing experiments such as, oh, look at this gas. When I pour it out of this container, it's going down. Therefore, gas has weight. No, that's relative to the air that it's in. Right?
What?
Right?
So then why does it have weight whenever it's in an empty helium tank?
Well, if you pour air into a vacuum, it would go in all directions. Hold on. If you pour air into a vacuum, it will go in all directions.
Look, Koso made a valid point.
So,
and I'm responding to it
again, you have a dispute. You disputed that it has actual weight, average weight, or gravitational weight. Like I said, if you're on a scale and you're in this bottle, you're in a big container, and you're doing jumping jacks, do you think I can tell your weight by you doing jumping jacks?
Well, there's as you land, there's added extra force.
If you're in there,
yeah, I think you could. I think you could. Yes. You'd get the maximum and the mid. Hold on, let me answer then. You get the maximum and the minimum numbers on the scale, and then you could probably work out something between the numbers.
So you could. So just because they're going omnidirectional doesn't mean you can't determine their weight. That's what you're telling me.
Yeah, pretty much.
Okay, so you just contradicted what you said.
No, but what I'm saying is they are omnidirectional.
Doesn't matter. You said
yes, it does.
Weigh myself.
Because my argument
you get actual weight by average weight. Now you just said that. Now
my argument isn't that gases be my argument is gases are omnidirectional. I'm fucking babbling here. My argument isn't what you're saying. My argument is that gases are omnidirectional. They don't have a downward bias. Your argument is they have a downward bias. My argument is they're omnidirectional. So you're just proving my point.
I didn't say they had a downward bias. I said they have a higher velocity downward.
Kosho said they have a downward bias.
So did Jeremy.
Kosho said they have a downward bias. I said they're omnidirectional.
Downward bias is as in the velocity, yes.
They don't have a downward bias. That's the end
velocity
of the argument.
Downward is greater than going upward.
That's the end of the argument. Brummy says something, so therefore end of argument.
The end. You just proved my point. You said they're omnidirectional. You just agreed that gas are omnidirectional.
Yeah, but with a downward bias.
Nah.
Yes, that's what we said.
They have an upward bias. They have an upward bias.
Okay, remember, I said it before. How many vectors are there? How many vectors are there with gases or anything inside that container? How many vectors? If it's omnidirectional, how many vectors are there? And there's force. Well, I'll give you the answer because I don't want to play a game with you. There's a directional bias, there's a directional vector, and there's also a force vector. Two vectors, both with a direction and a magnitude. You know the
force vector.
Force vector.
The force vector is you subscribing gravity to that vector. You're trying to add a vector to it.
No, I'm giving you the force. I'm telling you. I'm not saying anything.
No, you're trying to. It is showing you that it's there. It's there already.
There.
It's not that he's
we have a force vector. It's down. Gas has weight. That's what causes it.
I hear what you're saying.
So and it's omnidirectional because it's omnidirectional. Why? Because it's a gas. There's no Coulombic bonds holding these molecules together, so they bounce off each other in the walls of a container. And if there's no container, they bounce off each other if there's enough of them above them.
It's biased is to be in any direction. That's gases biased. It's not downward bias. It's in any direction.
You can fight it all you want, Romy, but this is the way it is.
Omnidirectional. And by actual
but a velocity greater going down. But a velocity greater going down.
That's you subscribing a pseudo force.
I'm not subscribing anything. I'm just telling you the way it is. Because otherwise, you tell me how we can impart a greater force on the scale on the downside versus the upside. And we've asked that question thousands of times, and you still can't answer.
I've already told you.
No, you said it's the shape of the container. Well, because everything kind of goes down. I don't know what you're saying.
Yes.
I can't repeat what you say because it makes no sense.
It doesn't.
You are covering. You are submerging it. You are submerging it in a container which does have a downward bias. and then saying
So
to
the
me,
container has a downward
gases
bias.
have, therefore, hold on. Therefore, gases have a downward bias because we're surrounding it in a downward bias material. That's what you're
This
saying.
makes no sense, dude.
That's
No
your
sense.
answer. That doesn't make any sense.
Yeah, your question just it's like, and so you like paper clips?
Exactly.
It just doesn't make any sense.
Remy, you should just back off a little bit. Let Jeremy take over because right now I think you're really confused.
No, you are confused. You're saying that.
No, I'm really not confused, actually.
Because we cover gases in a container, which is a solid. Therefore, every gas molecule inside the container has a downward bias because it naturally has a downward bias. Well, the only reason it has a bias downwards because you've covered it in a solid material, which is a container.
Why would it go up?
So weird, dude.
Why would it not go up as much as it goes down?
You can't because it's trapped in a container.
So why would it
be
equal everywhere?
You're asking
gas law. So
you are literally going in circles.
So gas law says that the pressure.
Wake up!
His experiment
Yeah,
doesn't
and it has a ground too. I mean, it always has a ground. So, do you think the ground causes an upward bias?
Sorry, what are you saying now?
Do you think the ground causes an upward bias? If you think the top of the container causes a downward,
what's the ground? What's the ground made out of?
Whatever, dirt, concrete, whatever the ground is you're standing.
It's a solid, right? We're talking about solids, liquids, and gases, right?
Yeah.
They're the three things you're talking about.
Yeah.
So what you're asking me
Sure.
does a solid have an upward bias?
I'm saying, does the gas striking the ground, does that give the gas an upward bias? Because you were saying the gas striking the top of the container gives it a downward bias.
You know, I don't really understand the question. Say it again.
For the opposite.
Well, why is it?
You said to me. You said to me.
Why is the gas?
You said to me.
If you don't understand,
originally, no. Your first question was: does the ground have a given upward bias? You said, does the ground give the gas an upward bias? So, do gases, do solids have an upward bias? Is that what I asked you? So your answer to that question would be no, right?
I don't know. What would you say? I would say no.
Well, solids obviously don't have an upward bias. No, of course not.
So then, how does the container give it a downward bias? I thought you said it was because it was bouncing off the top.
Because it's a solid.
Yeah. But how does it give the gas a downward bias?
Because it's
contained. How does it give that to the gas?
Okay, so if you put a container around the gas, right, the container has a downward bias. It would literally dominate the gas, giving it a downward preference, wouldn't it?
So because the gas bounces off the top, because it can't get out, basically, it's being held in by the top. It has a downward bias now.
It's captured, isn't it? So, for example, if I put a rope around you and run really fast, eventually the tension of that rope would cause you to go back with the rope, wouldn't it? Because you're being dominated by that force. So if the gas is just going in its own direction, if it's omnidirectional in its natural state, omnidirectional, no bias down or left, right, or up, it literally just goes in any direction it wants. Then you capture it, contain it in a complete container, and then it has like a force acting on it downwards. Then you're saying, oh yeah, no, the gas has a downward bias as well. The gas
so my question is
by the container.
Okay, I get it. My question though would be wouldn't the reverse hold then? So the gas near the ground, all that gas there, you say it's omnidirectional, except for the gas is right near the ground really isn't omnidirectional because it can't go down. It hits the ground and bounces upwards, right? So doesn't it have a upward bias right on there?
I know it's literally bouncing up on all directions. Yeah, I'd say yeah, of course it does. If that's what the gases don't have an upward or downward or left or right. Gases are omnidirectional.
Mic check. Can I offer a quick suggestion?
What you're saying doesn't make sense. Isn't consistent with what you're saying.
Are you saying gases aren't omnidirectional? Is that what you're saying? Because I think they are.
I'm saying the way that you explain the container seems to contradict what you're saying about the ground, but it's not a big deal, really.
If it hits the floor, is it a container? It's a surface, isn't it? The floor would be a surface, like the wall would be a surface, but a wall and a floor is not a container. It's a completely different.
I didn't say you said they're the same thing. I said the way you explain. I didn't say you said they're the same thing. I said the way you explained the downward bias caused by the container seems to contradict the lack of upward bias from the ground. I don't think it's that big a deal, though.
No, because you're saying a surface. You're saying a surface is the same as a container, which is not analogous.
No. I'm not saying the same. I'm saying the explanation. I'm saying the explanation that you offered for why it imparts a downward bias seems to contradict it. Not
well, no,
the same thing.
The reason I know you never understood what I said is because you said, "Oh, so the floor gives it an upward bias."
Well, I asked you if the floor would do the same thing because the way you describe the container is it holds it in, it stops it from going up. It's everything you say about it implies this sort of sense that it can't go any higher than the top of the container.
Is the floor is a floor a container? Let me ask you this. Is a floor
so the floor is doing the same thing in the reverse direction.
Is a floor a container?
I didn't say you said that.
I'm just asking you that question.
I know, but no, they're not the same thing. No one's talking about
Can
the same
thing. Can I get an answer? Can I get an answer?
What are you asking me? You just got your answer.
So obviously they're not the same thing. They're not the same thing. So why are you asking me? Would the floor?
Why do you keep trying to
switch the floor behave? Because I'm
saying that the explanation you gave. Here, I'm telling you that the explanation you gave for the container. Listen, the explanation you gave for the container seems to contradict what you're saying about the ground. That's what I'm saying.
The reason it seems to contradict it is because you're misunderstanding what's being said, and that's why I'm telling you your question was malformed.
Okay. I don't think it was.
Well, I'm trying to tell you how it was, but you're not allowing me. You're not allowing me to explain how it is malformed.
Sorry, between us, you're yelling in my ear, so I don't know how I'm stopping you. But okay, go ahead.
Because you keep saying that my question's wrong. At the end of the day, you're saying that the floor is the same as a container. It's not. When a gas is being contained by a container, well, so why are you asking me that question if the floor gives it an upward bias?
Because the explanation you gave for why a container.
No, you explained to me why. You explained to me why you're asking me that question. That's what I asked you.
I am.
You just say you said this. You explained to me what was going through your head to ask me the question why a floor gives a gas an upward bias.
Because the way that you
explain what you're understanding. Then explain your understanding.
Rummy, do you not hear yourself interrupting me as soon as I start talking every time?
How did I explain it? Then? Explain how. Explain.
Twice. I've just tried to, and as soon as I say because, you start interrupting. But explain it.
You say you keep saying the way you explained it. The way you explained it. Just explain what you understood from what I said.
Don't bully Rummy. If he's not answering your question, just let the conversation move on. Nobody likes to hear that stuff.
I think I am answering the question too.
Well, you're not. You keep telling me the way you explained it. Rather than telling me the way you explained it, just tell me what I explained. Tell me how you understood what I said. Don't just tell
can
me
you hear me?
That's what. Yes,
is a room a container?
Let's go then. Let's hear it, Scott.
Hold on. So
I'm trying to explain.
Hold on, Literally, please. We're having a conversation. Just I get your point, Literally, but you're missing our point.
But it's a good answer for a question. It's
can I finish? It's going to derail. It's not going to. It's going to derail my point, though. But you, all right, go ahead and take over if you want, Literally. But notice I have not yet got to finish this sentence.
White 19.
I don't think that's true. All right, so here's the explanation. You gave an explanation for why it is the container imparts a downward bias. Yeah, your explanation was that the air doesn't have anywhere to go. It's trapped by the container, right? You said the top of the container is what gives it a downward bias.
Sorry, disconnected. Sorry, disconnected. Okay. I'm disconnected. Sorry, start again.
This is fine. It's the same. I'm starting at the beginning. So the way I understand what you're saying is that the molecules of gas inside the container have a downward bias because when they're going up, they're going to hit a barrier, which is going to cause them to go down. And so that's going to cause them to go down more than not, right? I'm pointing out that when molecules hit the ground, they're going to not be able to go down anymore. They're going to go up. So if what you're saying is true for giving a downward bias for a container, it seems like a ground would give an upward bias for gas.
Yeah, but that's the ground itself.
Wait. How do you know there isn't equilibrium for stuff that goes down? There isn't equilibrium for stuff that goes up. We don't know.
Well, I'm just basing. I'm basing on what he told me.
I mean, that's right, Scott. That's right. The ground would also balance things off, and that's where you have like a net balance or something inside the container, right? It's a net weight. When all these molecules are balanced off each other, eventually they all balance out, like what she's saying with the equilibrium.
Right.
So eventually you'll get like a kind of an estimate of weight of the gases. Because they're all balanced off each other inside the container.
Why is it more down than up? That's his question.
Well, how many sides? Well, the fact that why is it more down than up?
Well, wait,
that's been the internal question today.
Wait, that can't be the question. Why is it more down than it's up? The fact that
it is the question.
Going up. No. The fact that helium and everything else and these certain gases that are going up in all directions is the problem. Because your down has an issue then. There is no force down in that equation, right?
That's true.
Stacy, no. Sorry. No.
No, Stacy, that's true. You made a good point.
But the velocity is going down at a greater rate of acceleration. Higher velocity going down. So the force is going to be greater when it hits the bottom, not the top.
Let me talk.
I'm in the middle. Broomy, you did it to Veach.
The bottom of the container is the only...
You gotta stop, Broomy. You gotta take a breath. It's just so annoying.
Sorry, go on.
So when the air molecules inside the container are going at a higher velocity going down, they impart a greater force on the container on the bottom, not the top. So yes, they could be going in all directions, but it's biased downward, as we've been saying.
The force is greater at the bottom. So tell me why, if the force is greater at Earth, then why
because the velocity is greater
in the first place? That helium should be going down. If
no,
the force is pushing everything down.
Yes, that's what makes it accelerate down and decelerate going up.
The thing that I don't get is you can
simple.
A tank
Lemon, before you confuse everybody, can we just get that mission
before you confuse everybody?
The only problem I have
electromagnetic variations of toroidal fields. Let's talk about this simple experiment. It's in a container. It's round. It's a ball, let's say, and it's got more force on the bottom than the top. It does. It means it can't be going equally every direction. It can't.
Prove it.
That's why you got a force at the bottom.
Prove it.
Only problem. At the bottom,
the fucking ball on the scale. You measure it. It weighs more on the bottom.
The ball on the scale is different. That's the only problem.
The only problem that I have is that helium goes up, but it's put in a huge metal tank that goes down, and all of a sudden you're registering more weight with something inside that's going up. That's a contradiction. Is it really weighing down on the scale and increasing the mass, or is the tank, I don't know, holding on to it tighter, and that tighter,
it's giving it a bear hug
in the tank being registered as weight on the scale? I mean, what's going on?
Those gases are moving in all directions. Isn't one of those directions going to be down? So isn't the scale measuring a downward vector?
But what about the helium in general going up, though? In general, helium goes up, not down.
Challenging the other shit like the gradient in the container, but y'all know gravity's real.
There's a force down, and there's proof of force down. That's your answer. But we don't need to be talking about that force down. You guys need to figure out and explain why the force. That there's things going up, like small things like helium. Right?
But helium in a container, helium in a container still goes down.
If I push down on the zit, which way does the zit? Stacy, if I push down on the zit can go up, right? If the force is around something greater than the force.
I didn't hear him. Sorry, I really didn't hear you.
You can't stop talking.
No, I really couldn't hear you. I'm asking you to repeat yourself.
If you push down on the skin around the zit goes up.
Just make all that noise.
Damn, stop making a salad.
It's Brummy.
Doesn't matter. I still didn't hear him. I think I'll ask my actual.
Brummy, you need to go on push the talk.
But you guys did have a point that there might be a bit of a force downward, but it's like me on the scale with the balloons. If I have like 100 balloons that I'm trying to hold, I'm going to hold on to them real tight, even though they're trying to go away from me. And that may still be registered as down on the scale because of the greater forces. I kind of pull in and try to, hold on to these balloons. What if that's happening with the tank and it's not necessarily adding weight to the scale, but there's now a new interaction as the metal tries to hold on to this, helium or whatever.
That doesn't happen.
They can test that. It can falsify that hypothesis.
Wait a sec, but if the gases in that container are moving omnidirectional in all directions, wouldn't the pressure be equal? Like even at the bottom, wouldn't the gases be pushing equally at the bottom as well?
Right. So why isn't it?
No bias.
Hold on, let me answer this
why
question.
Isn't it?
Let me answer Pope's question. You missed the part about the two vectors. Did you miss that? Did you just join us, Pope?
Yeah, I probably missed that.
Okay, so there's two vectors. There's a directional vector and there's a force vector. So yes, omnidirectional, yes, that's the directional vector. Force vector, one direction, down.
How do you differentiate between the force vector and the directional vector?
By how it's measured. You measure the force vector by on the scale. That's how you use scales to measure directional of a force vector. Sorry.
Better yet, what is the difference between directional? What is the difference between a force vector and you said directional vector?
Yeah, directional vector has a direction and to which way you're pointing.
Well, really, they're the same vector.
Yeah, vectors have directions as well, though. Vectors have directions.
You didn't let me even finish.
A direction.
It didn't let me finish.
That force has a vector. Yeah.
It's one vector though. You keep calling it two vectors. Really, it's one vector with a direction and a magnitude.
No, there's two. There can be a directional vector as well. That's the distance and the direction, and the force vector is the direction and the magnitude.
It's basically like a triangle.
Well,
With vectors, you're basically dealing with triangles. Basically, you have a plane that's going up with one side of the triangle, and then a wind vector could be the force pushing, kind of 30 degrees up into the right. And then when you connect those two lines, you're going to have a new directional vector that adds those two things together, where your plane is now going a little kind of further south by, that 30-degree force vector now in a new direction. I think that's what he's talking about.
No, you're driving.
So again, thanks for confusing everybody. So Space Pope, do you understand the difference between a directional vector and a force vector?
I sort of do. I just don't understand how the values would be different, though.
They're much different. So again, a directional vector would be like 1 mile to your house and it's east-west or northeast or something. That's the direction. That's the directional vector. A force vector would be this amount of force in this direction as well. So it could be same as the direction.
Right. So let's be more specific. Let's only talk about the force vectors. Why is it that the force vectors are different in the other directions other than down? Why is it that the downward force vector is more than
because the gas has weight? So you have the directional vector would be the distance between the floor and the ceiling, or the middle and the sides. Those would be directional vectors. And yes, gas would be omnidirectional, it'd be going in all directions. But the force vector for all these molecules is always down and has a value. And the value
it doesn't have to be stronger. Sometimes it can be the only vector left over if all the other vectors are counteracted. Sometimes it's the only vector left.
Yeah, man. I'm in the middle of a thought, and that's why you got to
Zanuck. You can say it over and over. You can say
every
it over and over,
time I say it, and Lemon jumps in, I got to say the whole thing again because he's
keep making.
How do you measure force vectors?
You put a scale as one apparatus that can actually do that.
Yeah, but a scale only measures downward vector. It doesn't measure other directions.
Force vector.
The downward force vector.
Yes, or sideways force vector. You can put it on the scale on the side of the wall. You can press on it and also measure. It measures force vectors. That's what it's designed to do.
No, it doesn't measure sideways. It only measures.
Yes, put a scale on the side of the wall, and you can measure things. Absolutely.
Okay,
the apparatus wouldn't register things
properly. You guys have not done that. You haven't
done
that.
You're not adding any value here.
Right?
Stop
wait, Zanuck, have you done that? Because Kosho says something about that. Taking a
yes,
and putting it on both sides and seeing that. Who has done it?
Anyone who's ever played with a spring has done it. You can have a spring works on a wall, on a ceiling. You ever see those kids with these springs on top of their head and they can jump and hit their head on the ceiling and get it bounce downward with the force?
I've never seen somebody
it's a spring. It just measures the force. By how much the spring compresses, that determines how much force was needed to compress the spring.
Okay, then how much force was needed, Zanuck? How much force was needed since you've done this? Tell me. Explain to me the numbers, please. Thank you. Seriously.
What? Explain what? Right? How many numbers what?
Explain to me what you got. What was the numbers when you did that then? If you measured that and you put
I step on a scale and I need exactly 100 kilograms force to react my weight. That's what the force is.
No. Let's go back to helium. We were talking about helium and doing that, and you were going to measure because this is a downward force, right?
Okay. Yeah.
So I want to see, because you said you can do this, and you have done this, and Coach has talked about this. Yes. Putting a scale on all sides of the container and measuring. So what is the answer for that? Please tell me. What'd you get? What were the answers?
Well, you have the weight. You have the weight of the same volume around something. So the weight of the air around the helium balloon, and then you get the weight of the helium balloon itself. Whatever is greater will stay down. Whatever is less will go up.
Exactly. I'm asking
hold on. Well, hold on. Whatever's lighter. Well, whatever's lighter.
He's trying to do that right now. You got to let him finish, and you got to understand too that it's going to depend on exactly what all he did.
Answering the question, and you know it.
I don't. It's not clear at all what you want to hear. I don't know what you're asking.
No.
Really,
I'll make it very
listening.
clear one time again. Then one more time. He was talking about, and so did Kosho, about doing this helium experiment in a container, or we can just put what scales on every single side, and we can measure that force. It's not just down and all that. Where is this experiment? And tell me the numbers and answers you got from that experiment that he said that he's done. Not a helium balloon.
Why is it?
Helium in a container, scales on all sides.
Scales on all sides. What do you mean by that?
Am I in?
Yeah, you're very confused. You're very
you guys
confused.
are the
What do you
ones
mean by
that
scales?
said you could put a
Scales
scale
on all sides.
all sides of the container and you can measure.
I didn't hear that. I didn't hear that part. Is that true, Zanik? Zanik, is that true?
We were talking about forces and how you can use a scale to measure forces. He said that's how you measure downward vectors, and you can measure. I said you can measure sideways vectors. You put a scale on the side of a wall and measure the force on the side of the wall. That's what I said. So now she's taking that and then thinking that's going to measure the gas.
We got our container. We got our container on the scale, right? Let's put one on the side and see the force of the gas pressing it on this against the side of it.
Wait, what?
Great. I'm glad you brought that up. So why will it not measure anything on the side of the scale, side scale? Why would it not? And I'll give you a hint.
Is the gas pressing on the side of the container?
Yes.
Yes, it is.
It is.
Absolutely. But why is it not measuring on the sides? Yes. I'll make it easier for you. I'll put a scale on one side, and I'll put a scale on the opposite side.
Listen, get some barometers.
Because that's not how scales work. Scales measure downward.
Why am I not getting? Hold on. I put 4 scales. I put one in front, one in side.
Danik, just let them answer now. You made the point. So why do you think it is that it doesn't register the side scales? That's the question. Because this is
that's
important.
not how scales work. They measure downward force vectors.
But why? What's going on?
Because they're not
there?
designed to measure sideways force vectors.
No, I put a spring. Let's use springs. We got a springs that's holding. Let's say picture a scuba tank.
Danik, don't overdo it. Just keep it simple. So there's nothing about a scale that doesn't work sideways. Just imagine a spring there. Now, why is it that it doesn't register a force or a weight on the sides? Why is it that's different about sides and down?
Probably because the scale is still going to want to point down if you put it on a wall. It's not made to work that way, probably.
No, we're saying build a spring there to just check to see if there's any tension on the spring.
That's
so
why I needed
imagine
to,
you have something
to clarify
just keep it simple. Keep it simple, Zanik.
But by not,
so what's the difference?
By not even letting
asking why do plumb bobs point down?
I have 4 springs holding a scuba tank upright. Okay, 4 springs holding it upward, and I got a spring on top, and I got a spring on bottom. So there's actually 6 springs. So why is the bottom spring the only one that's compressing?
Because springs are going to point down, like the plumb bob.
Is that your final answer?
I guess you'd have to make a helium weight where you compare it to how fast helium ascends to get an upward scale or something. I mean, we're talking like design issues here or whatever.
I have a container, and I fill it with helium, 5 kilograms of helium inside that container. I put it on top of that spring. I have 4 springs holding it upright, maybe one on the top too. What does the bottom spring actually measure? If we have it calibrated so that it moves 5 kilograms per inch, would it not be compressed by 1 inch if there's 5 kilogram force of weight inside of that container? Of course it would. It's exactly what it'd do. Wouldn't go side to side. It wouldn't go up. Gas is moving in all directions inside, but it has a vector down.
So we have 3 different options here. Either it is a force pulling down, it is a structure, number 2, or number 3, it's just the only option left over after all the other directions have been exhausted. Up, left, right have been exhausted and balanced out. The only other one that hasn't been is downward. So we have a couple options of how to look at this, from a gravity perspective or some sort of other perspective.
No other perspective needed. It's only one perspective. It has a downward force. It's an end of story. Gas has a downward force, whether it be helium, hydrogen, or anything.
So we have active force or a passive structure or a passive leftover, when all the other vectors and forces have been balanced out and exhausted, leaving only down.
Okay, this is getting silly.
We're not denying that gases have a downward force vector.
Oh,
you're denying that they don't have other vectors as well.
Well,
you're denying that you have other vectors is what I'm trying to say. My bad.
What has happened was the other way. They have been denying the downward vector for gas. They're saying there's no bias downward. That's what he's been debating.
You already said there is. So Good for you.
We're not denying it. We're just saying that there's
no, you
no
are not
bias
denying it.
in
They
one
are.
direction.
Brummy was definitely denying it. There's no doubt about it. He was very clear. He was denying it expressly.
Extremely clear, yes.
Well, it's easy to deny it when helium goes up in every other instance, and then all of a sudden you put it inside of a metal tank, and it's registering more downward weight. That's a contradiction. Is it still going up in the tank or not, or is it all of a sudden going down and pushing down on the scale?
Well,
it depends on the medium that's in.
Let me ask something real quick, Lemon. If I have that scuba tank and I put 1 gram of helium in that tank, is it going to float?
No.
If I put 5 kilos of helium in that tank, is it going to float?
As far as I can tell, no.
No matter how much helium I put in that container, is it going to float?
Not until it explodes.
Okay, so why would you think, how would it ever float? What would be one circumstance where that helium container, just the container itself, with helium, without it, can float? How can it float?
If it was made out of plastic like in a balloon?
Right. And why is that?
Because the balloon's plastic is not enough to overcome the force of the helium and weigh it down on a scale?
Not exactly. The reason is because the air around it, we can equate it to a pool to make an analogy even easier, but the air around it is heavier for that same volume as whatever is inside of that, whether it be helium or hydrogen or anything. So it'll always sink unless it's lighter than the air around it, then it will float. Just like
what did I deny exactly, Scott? I don't want to interrupt the conversation after Lemon's finished.
Does gas have a downward bias or not, Rummy? Does gas have a downward bias?
No, they were saying that you were denying that there's a downward gravity vector.
I don't think that gases have a downward bias. No, I think gases are omnidirectional, and that's it. That's my stance is my stance is that they don't have a bias. They're omnidirectional. Gases are omnidirectional. Not doesn't have a downward bias or a favoritism to downward. Only when they're contained by a container, then they'll have a downward bias. That's because the gases are contained. That's because gases are forced in a particular direction by the container.
Why is the container making it go down?
Because the entire container, the contents of the container will overall have a downward vector, wouldn't it? Every single side of that container and the actual container itself downward. I like Scott's point though about the bottom of the container pushing things upwards, which would be what creates the net force from as aware, right? There'd be a net force inside there, and that's because the gases that bounce off the bottom going upwards, and they kind of balance out. Hello, does anyone hear me?
Yeah, something weird's going on with Discord. I can't hear anyone else either.
It's because they're trying to censor the truth, bro. You know, when I speak the truth, it gets censored.
We can hear you. We can hear you. What do you want? What do you want me to? What do you want people to say? I heard what you just said, but there was not really. What do you want a response for it?
I want you to say sorry for muting me for so long. For muting me for so long.
I told you had a hot mic. You didn't respond like 3 times.
I put it on push to talk. After you muted me, I put it on push to talk, and then I sat here for 10 minutes.
You were so loud. You were like cleaning dishes or something. It was hella loud. You didn't respond. I had to mute you. That's how it works.
And as soon as I muted my mic and put it on push to talk, you left me muted for 10, 15 minutes.
I can't know that. You got to respond. You got to hit me up when you're back. I can't magically know you unmuted.
Check the fucking chat, bro. I tagged you about 1,000 times.
I did, bro. Well, check the chat when I'm saying hot mic and you're ignoring me, bro.
It's just because I've got the truth in it. You want to censor the truth, Scott? I get it, man. I get it.
I want to censor the truth of your dishes being cleaned. That's what.
Well, with weight, you're dealing with a bunch of vectors that combine to give us what we call weight. It is not anything with this set essence. Like this is just some magical atomic pebble that will automatically be pulled down due to gravitation. Depending on the number of forces in and around and going in and out of the object, you may have an object that rises. You may have an object that sinks. It is not this set property.
No, but